Welcome everyone. So now that we're finished with ionic bonding, ion formation, strength of ionic bonds, it's time to get into the really fun section of chapter 8, and that is covalent bonding. So in this initial lecture, I'm going to be covering just the basic principles of covalent bonding, and I'm going to be building on this in later lectures. So let's begin at the beginning. What do we know about covalent bonding? Well, let's start with the types of elements that are involved in covalent bonding, and that would be two or more non-metal atoms. Covalent bonding occurs between two or more non-metal atoms. And that's, of course, in contrast to ionic bonding, which of course occurred between metal cations with non-metal anions. Here we have two or more non-metal atoms. Now, how do covalent bonds form between these non-metal atoms? Well, they form whenever non-metal atoms do what? The magic word right here, share pairs of valence electrons. So let's highlight this as well. Share pairs of valence electrons. Now I'm going to note that this is also in contrast to the formation of ionic bonding. In ionic bonding, what happened was a transfer of valence electrons from metal atoms, which lost the electrons and became cations, over to the non-metal atoms, which gained those electrons and became anions, and then the oppositely charged ions bonded together. None of that's taking place here. Instead, we have non-metal atoms sharing. Sounds a whole lot more civilized, doesn't it? I'm going to underline this word share. It's a really important word. So the question is why? What is the motivation of our non-metal atoms to share pairs of valence electrons? Well, it's to become more stable. And how do they become more stable? By achieving filled valence subshells, just like their nearest noble gas neighbor. So we've seen before that having filled valence subshells makes an atom or an ion more stable. And stability is the goal of every element on the periodic table. This is just another mechanism by which an atom can get filled valence orbitals. So the list of elements below are a list of all of the important nonmetals on the periodic table that are frequently seen engaging in the formation of covalent bonds. Metals are not shown at all because we're dealing with covalent bonding, it's only nonmetals. So let's take a look at the elements we've got here. First, I want to draw your attention to the elements in the far right. And that, of course, is a list of our noble gases. And leading the top of this list of noble gases, we've got our friend helium. Now, helium, of course, is a noble gas, but it's a bit of an exception. Helium is a noble gas with just two valence electrons. And these valence electrons are in an s orbital. It's an s2 configuration, and that's because the only valence orbital of helium is its s valence orbital. Meanwhile, we have elements, let's get a different color, neon, argon, krypton, xenon, also in group 8a. However, these elements do have 8 valence electrons, just like their group number. So these all have 8 valence electrons, and these 8 valence electrons are in an s2 p6 configuration. S is filled with its 2 electrons, the 3p orbitals, 2 apiece, filled with 6 electrons total. And of course, we know that these elements are very stable, and that other elements would like to mimic this behavior. Now, let's take, for example, hydrogen. Whoops, let's get a highlighter. Highlighter for hydrogen. Boom, there we go. Now, hydrogen only has 1 valence electron. It's an S1 configuration. So when hydrogen forms covalent bonds, the goal of hydrogen is to end up with the same configuration as its nearest noble gas, which happens to be helium. So hydrogen wants to mimic the behavior of helium when it bonds. However, our other elements, our other nonmetal elements, well, they would like to mimic the behavior of their noble gases. So what we see are the elements in periods 2, periods 3, 4, and 5 over here, trying to mimic the behaviors of neon, argon, krypton, and xenon, these noble gases. Let's highlight these elements here. So these elements want to look like their nearest noble gas neighbors. Okay. Now, as it turns out, boron is a bit of an exception. Boron is an exception, and it's not going to do what we expect it to do. So I'm going to put a little asterisk beside boron and say boron exception. We're going to learn about the behavior of boron, not in this lecture, but in our next, is it our next lecture? Yes, our next lecture, you'll find out all about boron. Now, because the elements I highlighted in green are all trying to mimic the behaviors of either neon, argon, krypton, or xenon, they all want 8 valence electrons like their nearest noble gas, and we say that these elements obey the octet rule when they bond covalently. So let's note over here that these elements obey the famous octet rule. And that is because they want 8 valence electrons. Octet is the rule of 8. So, want 8 valence electrons when forming covalent bonds. But hydrogen's a little bit different. Since hydrogen's nearest noble gas neighbor is helium, well, helium only has 2 valence electrons, which means that when hydrogen forms covalent bonds, we say it obeys not an octet rule, but a duet rule. Obeys the duet rule, or a duet rule. Duet. Duet, of course, is a rule of 2. And we call this the duet rule because when hydrogen forms covalent bonds, it only wants 2 valence electrons. So let's write that down. Wants just 2 valence electrons. Okay. So now that we've sort of summarized the behavior of different non-metal elements on the periodic table, well, what do we get when various nonmetals form covalent bonds? Well, it says right here that covalent bonding results in the formation of neutral covalent molecules or polyatomic ions. So for example, covalent bonding could give us a molecule such as SCl6, sulfur hexachloride, or perhaps a molecule like N2H4, dinitrogen tetrahydride. These are examples of neutral covalent molecules. And if you notice, what are the elements that they're comprised of? Well, sulfur and chlorine are nonmetals. Nitrogen and hydrogen are nonmetals. They come together, they're sharing electrons, forming covalent bonds, and the result are these neutral molecules. But covalent bonding can also produce polyatomic ions. So polyatomic ions such as CO3 negative 2 carbonate, or say SCN negative 1 thiocyanate. So if you look at the elements in carbonate, carbon and oxygen are nonmetals. Well, what's holding the carbon atoms and the oxygen atoms together in carbonate? Oh, it's covalent bonding. The same thing is true of the sulfur, the carbon, and the nitrogen and thiocyanate. All nonmetals, what's holding them together? Covalent bonds. Okay, now one of the easiest ways to illustrate the basic principles of covalent bonding is to use Lewis dot symbols. Our good old Lewis dot symbols can be used to illustrate the principles of covalent bonding. So let's take a very simple example to illustrate. Let's take Br2, diatomic bromine. That's a bromine atom bonded to another bromine atom. So let's write the Lewis dot symbols for bromine. We have 2 bromines, so let's write it twice because we're so nice. So bromine is in group 7A. Group 7A. Group 7A. Which means the bromine atoms have 7 valence electrons, which we can depict I'm going to use different colors because colors are fun. Let's put 7 valence electrons around this bromine on my left-hand side. And I'm going to use a different color. Let's put 7 valence electrons around the bromine atom on the right. Now, both bromines would really like to have 8 valence electrons. If they had 8 valence electrons, they would have the same electron configuration as krypton, and they would have filled valence orbitals and be quite a bit more stable as a result. But the problem is neither bromine atom is willing to give up a valence electron to the other bromine. In other words, purple bromine isn't going to give an electron to red bromine. Red bromine's not about to give an electron to purple bromine, okay, because that doesn't advantage the giver. It advantages the taker, but not the giver of the electrons. So what's an atom to do? Well, if you can't give and take, there's only one other option for our atoms, and that is to share. Turns out since both these bromine atoms has an unpaired electron, they can share their unpaired electrons. Now, if they share their unpaired electrons, well, what do we end up with? Well, we end up with a molecule of bromine. So I'm going to push these two bromine atoms closer together. Now, the unpaired electrons become a shared pair in between the two bromine atoms, which I'm going to draw like this. Now, the remaining electrons did not get shared, so I'm going to put them back on each of the bromine atoms as they were before. So there are all the red ones, and let's get all the purple ones in. So here's the result. Now let's take a good look and see what we have here. Let's use some highlighting colors. So let's take this bromine on the left. All of the valence electrons around the bromine on the left could be claimed by the bromine, including the shared electrons. So all of its original electrons plus the extra shared electron is now the bromine's atoms, now belong to the bromine atom on the left, which means this bromine now, as a result of sharing, has 8 valence electrons. Well, the same is true for our bromine on the right, red bromine. So red bromine over here also can claim all of these valence electrons, meaning that it too has 8 valence electrons, 8 to the left, 8 to the right. Now, this means by sharing, both bromine atoms now have the same configuration as krypton. So by sharing, both bromine atoms have 8 valence electrons like krypton. That's their nearest noble gas neighbor. Now, we have special names for the electrons that are participating in the formation of that covalent bond. So the formation of that covalent bond comes about as a result of the shared pair in between the two atoms. So let's just make a word about this shared pair. So this shared pair, which results in the bond formation, is known as a bond pair of valence electrons. So that is a bond pair of valence electrons, and without that shared pair, there would be no bond between the two bromine atoms. So very, very important. So we've got the shared pair right here. But each bromine atom has a number of electron pairs that didn't get shared at all. So, for example, this pair of electrons on red bromine, this pair of electrons did not participate in bond formation. It's an unshared pair. Sometimes it's called a non-bonding pair because it's not participating in bond formation. But a much more common name for this pair of electrons is a lone pair of electrons. And so our electrons can be divvied up either as shared pairs, bond pairs, or unshared pairs, lone pairs, when we show the bonding, the covalent bonding between nonmetal atoms. Okay, well, let's do another. Let's take, for example, let's see what I picked here, H2S, hydrogen sulfide. So hydrogen sulfide is comprised of a sulfur atom, which is in group 6A, along with two hydrogens. Hydrogen, of course, is in group 1A. So I'm going to draw hydrogen twice because, well, we've got two of them. Now, let's find a new color. So the sulfur atom has 6 valence electrons. Let's put the 6 valence electrons in for sulfur. 1, 2, 3, 4, 5, and 6. Two pairs that are adjacent to each other and two singles. Meanwhile, hydrogen in group 1A has 1 valence electron. 1 and 1. Now, each of the hydrogens would like one more valence electron. With one more valence electron, they have 2, and 2 is what they want because hydrogen obeys a what? A duet rule. But sulfur wants 8 valence electrons. If sulfur gets 8 valence electrons, it's going to have the same configuration as argon. So how are they going to manage this? Well, the best way for them to manage and get what they want is to share their unpaired electrons. So these 2 electrons can be shared, and these 2 electrons can be shared. Now, if we share these electrons, well, what do we end up with? Well, we end up with a molecule of hydrogen sulfide. Let's draw that. So let's put sulfur here, and I'm going to put in sulfur's original valence electrons and its unpaired electrons. Then I'm going to take hydrogen and move hydrogen up close. Push the hydrogens in close and bring their unpaired electrons to pair up with sulfur's unpaired electrons. And so now, what do we get? Well, we've got ourselves a nice little molecule. So here's the sulfur now. And how many valence electrons does it have in total? Well, by sharing, it now has a total of 8 valence electrons, just like argon. Meanwhile, each of the hydrogens, here's hydrogen number 1, here's hydrogen number 2, each of the hydrogens now has 2 electrons, a pair of electrons. That's all they needed to obey the duet rule, just like helium. So let's note, by sharing, sulfur obtains 8 valence electrons, like argon, and the hydrogen atoms obtain 2 valence electrons, like helium, and all the atoms are now much happier and much more stable is really what they are, because obviously atoms don't have emotions, not like we do. Let's do one more like this, just one more. Let's do another diatomic molecule. Let's do diatomic nitrogen. Diatomic nitrogen. So diatomic nitrogen is obviously formed by 2 nitrogens bonding together. Nitrogen is in group 5A, which means each of these nitrogens has 5 unpaired electrons. So 1, 2, 3, 4, 5 unpaired, sorry, not unpaired, 5 valence electrons to a 1 pair, 3 singles in the Lewis dot symbol for nitrogen. And my other nitrogen, same deal. A pair, 3 singles. There are the 5 valence electrons on my other nitrogen. So once again, each of these nitrogens would like filled valence subshells. Both of these nitrogens can only obtain filled valence subshells if they get 3 more electrons. If either of these nitrogens gets 3 more electrons, they will have 8 valence electrons like neon. But blue nitrogen's not going to give away any of its electrons to red. Red's not giving up any of its electrons to blue. What's an atom to do? What's a nitrogen atom to do? It's got to share. And as it turns out, both of these atoms have 3 unpaired electrons that can be shared. And so we can share these 2, we can share these 2, and we can share these 2 electrons. So we'll end up getting 3 shared pairs. And what's that going to look like? I'm just going to draw it a little lower down here. Well, let's put the 2 nitrogens a lot closer together now. And my original nitrogen, let's call it blue nitrogen over here, with its unshared pair, and then the 3 electrons that are going to have to get involved in sharing, I'm going to pull over here. Meanwhile, red nitrogen, here's its unshared pair, its lone pair, and here are the 3 electrons that were going to participate in the bonding process. So what do we have now? Well, now the nitrogen on the left claims all the electrons, including the shared pairs in between, as its own, which now gives nitrogen on the left a total of 8 valence electrons. And the same is true for the nitrogen on the right. The nitrogen on the right also now has 8 valence electrons. So let's note by sharing, both nitrogen atoms have 8 valence electrons, like in this case their nearest noble gas neighbor, which is neon. Okay, that's not so bad. All right, trying to share electrons in order to get either an octet, for example, bromine, sulfur, nitrogen, or a duet like the hydrogens in H2S. Not so bad at all. Now, Lewis dot symbols are used to illustrate these basic principles. But moving on in this chapter, we're not going to be using Lewis dot symbols to illustrate covalent molecules or polyatomic ions. Instead, we do an adaptation of Lewis dot symbols called Lewis structures. Lewis structures are what we're going to be using from now on to draw representations of covalently bonded molecules and polyatomic ions. So how do we take our Lewis dot symbols and turn them into Lewis structures? Well, actually it's very easy. As it turns out, in a Lewis structure, bond pair, which I like to abbreviate BP, electrons are represented with lines, while lone pair LP electrons are still represented with dots. So for example, for diatomic bromine, well, how many bond pairs did we have? Let's go back, bond pairs. Oh, we had 1 bond pair, and I actually circled it in yellow. So that 1 bond pair is now going to be represented as a line between, whoops, that's a horrible line. Let's try that again. As a line between the 2 bromines. There we go. Meanwhile, all of the lone pair electrons around each of these bromine atoms still represented as dots. And so I had them, what is purple and red. So these purples are still going to be purples. Obviously, you don't have to color code anything when you do it yourself. And these were red over here. So they're still dots. It's just the bond pair electrons that ended up being replaced and being drawn in as a line. And what does that line represent? That line represents a covalent bond. So that's your covalent bond. Meanwhile, for H2S, if I wanted to do the same thing for H2S, we had sulfur, and there was a bond pair between sulfur and the hydrogen off to the right, and there was another bond pair between the sulfur and the hydrogen that was going down. And the sulfur had a number of unshared lone pair electrons on it, which we're still going to represent as dots. And notice those dots stay together. They're always in pairs. So you can't just redistribute those dots in some sort of artful, beautiful pattern. No, they've got to stay together as dots. And, well, what about diatomic nitrogen? Well, diatomic nitrogen had 3 bond pairs between the 2 nitrogens. Each bond pair gets replaced with a line, and so now we're going to have 1, 2, 3 lines between the nitrogens, and then we're going to put a lone pair on each of the nitrogens. And what do we call these structures? They're called Lewis structures. And in the next lecture, we're going to learn how to draw Lewis structures without having to, without having to do what I did over here. Because while this is a very good technique to show the principles of sharing valence electrons, it's not such a good technique to draw Lewis structures, especially for more complex molecules. And so we'll be talking about that in our next lecture. Now, if we look at the three molecules that I've drawn above, all right, you might notice that nonmetal atoms can share different numbers of valence electrons. So in bromine, we see that the two bromine atoms are sharing one pair of valence electrons. And whenever that occurs, we obtain, of course, a single bond. It's also possible for two nonmetals to share two pairs of valence electrons. And in that case, we obtain a double bond. And as it turns out, the maximum number of pairs of valence electrons that can be shared by just two atoms is 3. So this is the maximum. We can never go above 3, and that leads to the formation of a triple bond, which is, of course, what we have over here for diatomic nitrogen. Diatomic nitrogen. Now, it turns out we see some rather interesting trends when we examine single bonds, double bonds, and triple bonds. And one of the major trends that we see is that we go from a single bond to a double bond to a triple bond. Well, the bonds get stronger. A single bond is weaker than a double bond in general, and a double bond in general is weaker than a triple bond. So going from top to bottom, here, actually, let me give myself a little more space to write. So I'm going to say we're going here from weakest to strongest. In other words, bond strength is increasing, going from single to double to triple. But something else happens. Turns out as bonds get stronger and stronger, the bonded atoms get pulled closer and closer together. And because of this, we see another important trend, and that trend is that single bonds tend to be longer. And as we go down this list, triple bonds tend to be shorter. So this is not just a list from weakest to strongest bonds, it's also a list from longest to shortest bonds, which means that bond length is decreasing. Okay, so we've now taken a look at some basic fundamentals of covalent bonding, that nonmetals are involved, that they're in the form of atoms, that they, like metals and nonmetals, when they form ions, want stable noble gas configurations with filled valence orbitals, but they are achieving that by sharing pairs of valence electrons. That most nonmetals want a total of 8 valence electrons, but not hydrogen, and that's because hydrogen's nearest noble gas neighbor is helium and only wants 2 valence electrons. And we've seen that atoms can share 1 pair, 2 pairs, up to 3 pairs of valence electrons, forming single, double, and triple covalent bonds. Okay, well, the one last thing I want to talk to you in this introductory lecture on covalent bonding is the issue of bond polarity and electronegativity. So we know that bond pair electrons are the electrons being shared, but sometimes they're not shared equally. Now, it turns out that if those bond pair electrons are shared equally, which doesn't always happen, the covalent bond is then described as a non-polar covalent bond. But sometimes those bond pair electrons are not shared equally, so we can say that they are unequally shared. And in this case, the bond that is formed, the covalent bond is formed, is described as a polar covalent bond. Well, what does it mean by equal sharing and unequal sharing? Well, if bond pair electrons are equally shared, they would be found right in between the two bonding nuclei. But if bond pair electrons are unequally shared, they're not right in between. They're a little bit closer to one atom and a little bit further away from the other atom. Now, turns out what causes bond pair electrons to be shared either equally or unequally is a property of bonding atoms called electronegativities. So it says here, this is determined by the electronegativities of the bonding atoms. So let's define electronegativity. Electronegativity, really long word, so I'm not going to write it out a million times, is given the symbol, well, it's an uppercase stylized X. That is the same X that you used when you were learning about mole fraction way back in gases in chapter 5. And it's a Greek letter chi. So this is called chi. And that's a hard CH, chi. Electronegativity, chi, is a measure of the ability of an atom to attract bond pair electrons towards itself. And what I have here is a partial periodic table that shows electronegativity values for various elements on the periodic table. Now, the elements that we're interested in the most, of course, are the nonmetals. And the nonmetals over here on light yellow as opposed to green, and of course hydrogen on the other side of the periodic table is also a nonmetal. Now, you don't have to memorize these electronegativity values. What you should notice, however, are the trends in the electronegativity values. And one of the things we should note is that as we go from left to right across a period, what happens to these values? Well, they're getting bigger. They are increasing in value. And so that's the first thing I'm going to note here. So I'm just going to go from left to right here, and I'm going to note that electronegativity increases going across a period. Meanwhile, if we go from top to bottom down a group, so boron, say aluminum, gallium, indium, thallium, well, for the most part, and there are going to be some variations, what we see is an increase in values, other way around, a decrease in values going down a group. So down a group, all right, the general trend is electronegativity decreases. Okay. Now, turns out, based on these trends, the most electronegative element on the periodic table is fluorine. And I find that a very useful thing to remember. So fluorine has the highest electronegativity of all the elements on the periodic table. And I'm also highlighting fluorine because, of course, fluorine is a non-metal involved in covalent bonding. And so an easy way to remember just general trends is to remember that, well, fluorine has the highest electronegativity, so an element further away from fluorine will have a lower electronegativity. And the further away it is, the lower its electronegativity is. Okay. Now, notably, there is a group of elements not listed here with this periodic table shown. And that group of elements is the noble gases. The noble gases aren't shown here. Well, why is that? Well, electronegativity is described as the ability of an atom to do what? Attract bond pair electrons towards itself. Now, one of the things we know is that noble gases typically don't get involved in bond formation. And if they're not forming bonds, they're not about to be attracting bond pair electrons. And so in general, we consider the noble gases to be non-electronegative. So noble gases in group 8A are non-electronegative. And I'm going off board here. They're non-electronegative. Another way to say that is, all right, we treat their electronegativity values as essentially equal to 0. what about the units for these electronegativity values? Well, they do have units. We're not going to be concerned with the units. It's way beyond the scope of this course. So I'm going to note that we're going to treat these electronegativity values as if they're unitless values. So treat electronegativity values as unitless. Okay, so we've seen some important trends in electronegativity. We know fluorine has the highest electronegativity now, that noble gases are essentially zero with their electronegativities, and we've defined electronegativity. But how does electronegativity allow us to figure out whether bond pair electrons are equally or unequally shared, or whether a covalent bond is polar or nonpolar? Well, let's scroll down and take a look at that. And well, here's our answer. As it turns out, for two covalently bonded atoms, the bond pair electrons will be pulled slightly closer to the atom with a higher electronegativity and slightly away from the atom with a lower electronegativity, resulting in unequal sharing and a polar bond. Well, there we have it. So let's take a look at some examples, and I'm going to fall back on the examples we've already done in this lecture. So let's go back to bromine. Diatomic bromine, Br, Br, and I'm not going to draw it all colorful this time. I'm just going to use the black pen. Okay. Now, if we look up on our table, we can look up the electronegativities of these two bromine atoms, and I'm going to get a sneak peek here. Where's bromine? There it is. It's 2.96. 2.96. Let's write those values down. 2.96 for this bromine, 2.96 for this bromine. Now, that line in between those bromine atoms indicates a shared pair of electrons. Now, since the two bromines have the same electronegativity, they're pulling on those bond pair electrons with equal strength. And so are the electrons going to be further to the left, further to the right? No, they're going to be right in between. So there's that shared pair of electrons. And so I can say over here that the bond pair electrons, on average, are right between both bromines. And of course, this means that the electrons in that bond are equally shared, and thus this is a non-polar bond. So, non-polar bond, and that's because the bond pair electrons are equally shared. Now, in contrast, we could then take a look at H2S. H2S, sulfur, hydrogen, hydrogen, and two lone pairs on the sulfur atom. Now, once again, we can go and look up the electronegativities of sulfur and for hydrogen, and I actually memorized them in my last sneak peek. Hydrogen has a value of 2.2. So 2.2 there, 2.2 here. Meanwhile, sulfur has a value of 2.58. So here, the sulfur atom clearly has a higher electronegativity than hydrogen. So let's take a look at this bond right here, the bond that's going off to the right. That pair of electrons is going to be pulled slightly closer to the sulfur and slightly away from the hydrogen, like so. And the same thing is true for the bond that is going in the downward direction. This bond over here, again, because sulfur has a higher electronegativity than the hydrogen, those bond electrons are being pulled closer towards the sulfur and away from the hydrogen. And so here, clearly those bond pair electrons are not being shared equally. So let's note that our bond pair electrons are pulled closer to sulfur and away from hydrogen. And the result is that we have two polar bonds in which the bond pair electrons are unequally shared. Okay. Sometimes to indicate that bond pair electrons are unequally shared, well, we don't actually draw a picture like this. So first of all, I'm just doing an illustration here. When you draw Lewis structures, you're not going to show anything like this later on. But we use another notation sometimes to indicate polarity in bonds. And I'm just going to redraw my H2S molecule. And because those bond pair electrons are closer to sulfur, so they're being pulled over towards the sulfur, and well, electrons carry negative charge. Because those negatively charged electrons in the bond are a little bit closer to sulfur, sulfur ends up acquiring a very slight negative charge. And we show that slight negative charge by using the Greek symbol delta. And that's a lowercase delta followed by negative. Delta negative. And that shows that sulfur has a very slight negative charge. Why? Due to the proximity of those bond pair electrons. But it's the opposite for the hydrogens. The hydrogens have had the electrons which are negative pulled away from it, and so the hydrogens end up getting a very slight positive charge as a result. And so sometimes we show, all right, a charge distribution in a molecule because of the presence of those polar bonds in the molecule. Now, one last thing to mention in this lecture here, and that is this, that as the difference in electronegativity increases for a particular bond, the polarity of that bond also increases. So what do I mean by delta chi? Delta chi is the difference in the electronegativities of the bonded atoms. So for example, let's go back to bromine. Well, delta chi for the bromine-bromine bond would be, well, each bond has an electronegativity value of 2.96. 2.96 minus 2.96 equals 0. So there is no difference, which is why the bond is nonpolar and the electrons are shared equally. As it turns out, we will always get a delta chi value of 0 for a nonpolar bond. In contrast, let's take a look at delta chi for the sulfur-hydrogen bond. Well, sulfur has an electronegativity value of 2.58. Hydrogen has an electronegativity value of 2.2. And so when we subtract, we're definitely getting a non-zero value. For the sulfur-hydrogen bond, it is 0.38. So now we have a polar bond because there is a non-zero delta chi value that's obtained. So this is a polar bond here. Now, the notation here tells us is that as delta chi increases, bond polarity increases. So let's suppose in this molecule, instead of having sulfur here, we had an oxygen. What would delta chi be for, say, an oxygen-hydrogen bond? Well, if we look up on our chart of electronegativity values, we would find that oxygen has an electronegativity of 3.44. And if we subtract that from hydrogen's electronegativity, sorry, the other way around, we're subtracting the 2.2 from the 3.44, well, what do we get? In this case, for an oxygen-hydrogen bond, we get a value of 1.24, which is also a polar bond. So both a sulfur hydrogen and an oxygen hydrogen bond are polar, but they don't have equal polarity. Turns out that the bond polarity is increasing here because the delta chi value for OH is a higher value than the delta chi value is for an SH bond. So let's note here, bond polarity increases. And what we're comparing here is this value to this value. The higher the delta chi value, the greater the bond polarity. Okay, so we've done all of the introductory level stuff for covalent bonding. Next time we're going to jump in and start drawing Lewis structures, which is super fun. Can't wait to do it with you. So until then, take care, and I'll be talking to you soon in our next lecture. Bye now.